works. Thanks everybody. I'm going to talk about a topic that kind of is a little depressing sort of in the long run, interference globally. I'm John BRAUN, I'm in the Cosmic program at UCAR. We are a radio occultation processing group. Radio occultation, there were a couple of talks in the climate section yesterday about RO. But radio occultation is basically the limb sounding of the atmosphere using GNSS signals. It has been around since the first time it was demonstrated was planetary missions in the 60s, but limb sounding of the atmosphere, of the Earth's atmosphere, has really been around since about 1995. Our group processes data from a number of missions, including the Cosmic 2 mission, which I'll be talking about, which is a constellation of 6 satellites in low Earth orbit. What impact does this have on forecasting? Here's a result recently from Catherine Lonitz at UCMWF that's basically a score called a Forecast Sensitivity Observational Impact Score. So it's basically how much each observation is impacting a forecast at any one time. And it's ranked from basically most important to least important. And RO right now is sitting at number 3 in the global data assimilation community behind only microwave temperature and microwave water vapor. That's a pretty impressive metric. It's weighted by the number of observations, so about 10,000 RO observations go in a day. The microwave temperature and water vapor sounders are imager observations. They have just lots more data that go into it. But RO is becoming more and more important in the global NWP community. So I was talking to somebody yesterday, and they were like, "Why are you here? You're not really in the geodata community anymore." And I just kind of want to say that we are sitting in kind of this area. This is from a National Academy's report that was came out in 2020, and it sort of demonstrates where the IGS sort of sits in all of this global remote sensing sorts of thing. And that, the IGS is the infrastructure and the terrestrial reference frame and the geodetic products that are sitting there, and all of the science that derives, that I sort of deal with, is based on what the IGS and on the rest of the international geodesy community is providing. So I'm sort of in this radio occultation set, sort of halfway up the food chain. How do we use the IGS? Well, we use the ultra-rapid orbits for all of our real-time processing. We process GPS, GLONASS, Galileo, Beidou observations. We use data from the IGS ground network for our clock estimation strategies. We host an IGS N-Tripcaster to help basically provide a little bit of service to the IGS community, but we also use those streams for our own processing. Real-time is important for us, so we have a latency requirements for the ionosphere of 30 minutes. So that's 30 minutes from the time of observation on the spacecraft down and delivered to the operational data centers. So, in 30 minutes, about 25 minutes of that is basically sitting on the spacecraft. So we have a lot of requirements. We are a 92% uptime, so we're greater than 92% of reliability. So we are sort of sitting there and we rely on the IGS quite extensively. Here is a satellite that I think about the most. This is a Cosmic 2 satellite from Formosat 7 in Taiwan. And I'm going to talk about a number of different instruments here. This is the RAM side of the spacecraft, so this would basically be flying at you. There's a POD antenna here. This is basically a standard Dorn and Margolin element with a few choke rings on it. There is an exact replica one on the backside. So there's 2 POD antennas, one on the fore and one on the aft. They are mounted basically 15 degrees above the RAM velocity. A terrible antenna configuration for POD. But really this is more than just POD, is that we're profiling the ionosphere. So we fly at about 550 kilometers, and from the POD antenna, we are tracking from basically zenith all the way down to about 100 kilometers tangent point altitude. So we are profiling the F layer of the ionosphere for space weather applications. Here is a neutral atmosphere, a 12-element limb antenna for our neutral atmosphere profiling. There's the same sort of limb antenna on the backside. So we are collecting, each one of these spacecraft is collecting about 2,000 neutral atmospheric occultations a day. There are a couple of other payloads here. This is an in-situ ion velocity meter, and there's an RF beacon transmitter here that's going down, that's transmitting to the ground. So this is a plot from Max Roberts. He was at JPL, now he's moved on to Muon. And this is basically, what does our SNR look like over a day from the POD antenna? And the green is basically would be the 4 antennas, so what you see coming at you. The red would be what you see at the end. And so, these are volted, these are SNRs in volts per volt, so they just sort of look fine. But if you detrend these things, you sort of see these little features here. And like, well, what's going on here? So if you would zoom up on one of these features, you sort of see that in the SNR, you have a whole bunch of this sort of crapola sitting up here. And if you detrend that, you sort of see a really common sort of amplitude signal or periodic signal on the 4 antenna, and then it switches over to the aft antenna. And really what this is a jammer on the ground sitting there, and the GNSS receiver in space is sensing that signal. It's sensitive to, that jammer signal is going into the POD antenna, and that's affecting all of the satellite that is tracking there. This is important for us for a space weather application, measuring ionospheric scintillation. So Max developed this algorithm, we have implemented it, and we processed it, we compute basically what we would call an RFI index for every track that we come down. I thought that I would just generally talk about this when I was preparing this abstract, and we're starting to move on here. And so, I'll just sort of skip this one. This is sort of in a day. So we have basically 14 orbits a day, 15 orbits, and you just sort of we see these same sort of events in a very periodic signal. So we're sort of seeing the same ground sources every day. Here is a 2022 RFI map. So this would be the 4 antenna, and this would be the aft antenna. We've implemented another algorithm developed by the Aerospace Corporation. And so if you sort of see what we have here, that's the little yellow part would be where we're identifying RFI on the 4 antenna and RFI on the aft antenna. So you sort of see, it's in a spot where you wouldn't really expect off the coast of California or Mexico, but it's there. And how does this look? So this is in our measurement, these are in our amp. This is our RFI index here. Elevations are plotted here in colors, so 80 degrees basically the zenith. Spacecraft elevation is here, and we track to about minus 25 degrees elevation angle. As we fly over one of these things, we sort of see a real depression in an SNR, and this impacts an S4 index, which should be a measurement of ionosphere or atmospheric scintillation. So I thought I'd just be talking about this. You sort of see it here on the 4 side, and you see it here on the aft side, and you can really locate where these sorts of things are sitting. It's kind of a surprise. And then this is 2024. So this is just from a couple of weeks ago. You have another RFI source here over Africa. This is the 4 side of the antenna, or this is the 4 side of the spacecraft. This is the aft side. You have our RFI index here. We have all of this sort of stuff going on. It's sort of the same looking thing. Lots of signals here. And at this point, the S4 index is not as elevated. I will just say here is really elevated S4 due to the ionosphere, and that is an ionospheric scintillation event. That's what it looks like. And then, but we we're looking at a new version of the TGS flight software. And so there are times when we really have terrible SNRs on our POD antennas. And so we started averaging basically in 3 degree by 3 degree bins here is I think what we did. And so we started averaging up basically our nominal SNR. Here we go to about 500 volts per volt. And we see a couple of regions here where we have really depressed amplitude, or SNR amplitudes. And that's kind of depressing. This basically, and if you would start reading around in the news, in the aviation industry, this is really well reported. There are hard times flying airplanes here. And so we're seeing all of this RFI from space. We see it on GPS, we see it on GLONASS. We are tracking Galileo, but just in the neutral atmosphere. So I don't have any Galileo results here. We're just we're still collecting enough data to see. But there is really a global distribution here of RFI, and it impacts integrity monitoring, it impacts applications, and I think that it's a serious issue. So now I'm going to switch over to the RO antenna. So the radio occultation antenna is designed to maximize gain at the limb of the atmosphere. So it is tracking from about 100 kilometers tangent point altitude down to about 200 kilometers negative tangent point altitude here. And so I didn't say this, but the C2 spacecraft are at an inclination of 23 degrees elevation. So we basically see occultations in the neutral atmosphere to about 40 degrees latitude. So we don't get full global coverage on this. But we see, we have the sort of same, this is our SNR average on L1 SNR, L2 SNR, and we sort of see these spots here of degradation. The plot that I had before was basically the spacecraft subpoint. These are the limb geometries. So this is the tangent point of the neutral atmosphere. So the position is a little bit different in space, but the same sort of sources are going on. And then here are two metrics that we have, basically of our QC metrics of how our data quality looks. And so you can sort of see these are in units of microradians, so it's a bending angle measurement. So in these two regions, we have increased bending angle noise. This is not really affecting our the data assimilation right now. It's still within our requirements, but that noise level is definitely increasing. We see it. And this is the standard deviation with respect to climatology. We sort of see that noise going up. And this is this measurement is at 30 to 60 kilometers. It's sort of at the top of the atmosphere, and we use it as sort of a noise metric of what our observations are. So this is, if you just break out GPS, this is what the GPS looks like. It's sort of here. We have lower SNR on our L2, but you can, L1 is really our basic retrieval frequency, and you just see it in our noise. It's just sitting right here. I'm getting close to being done. I'll talk about GLONASS as a similar sort of thing. We don't quite see as much noise in our two error metrics here, but it's there. And then I'll bring up another constellation that we'll process. So Spire is a commercial company that's providing commercial data for the community. They have global coverage, and they collect data, GPS, GLONASS, Galileo, and you can sort of see there's fewer observations for this, but this is basically, you see the Ukraine right here. That we're not getting any Spire observations over the Ukraine. So these sorts of global conflicts are impacting us. So in summary, RO missions are really atmospheric sounding missions, but they have a kind of a unique configuration to observe RFI on a global scale. Our POD antennas are sort of field of view sorts of things. Our limb antennas are mounted to look right at the limb of the atmosphere. And we are observing RFI, and we're trying to figure out how we're going to mitigate it on a global in our processing systems. This impacts both our neutral atmosphere and our space weather products. If you would just do some regular Googling, you can see that this is a very serious concern for the aviation industry. And it sort of has impacts here for monitoring and integrity issues.